All right, so let's get started on some of the notes here. It's going to still be based on the stuff we started last week, which is circular motion. I know on Monday and Tuesday we talked about how to convert radians into degrees, degrees into radians. Okay, we did all that. On Wednesday and Thursday, we introed the new stuff where it was circular motion. Where you're actually traveling along an arced path. I think we did a Ferris wheel problem at one point. We did, I think, another one on Thursday where we introed it. Today we're going to be really focusing on that today and kind of talking about kind of the numbers that are involved. So we're going to go into to that stuff. The formula you need today before we begin, the formula we're going to use for pretty much every single problem is this formula right here. This is the one that you're going to want to write down. It's the one that we're going to basically use on every single problem. There might be one or two problems that ask you for something different. But this is the formula that we're going to use strictly from now on, for this section anyway. This is called the arc length formula. If you don't remember from last week, arc length is that path that you're traveling on a circle, right? It's that distance traveled. Now the S is the arc length itself. It's the distance traveled. So it's so many inches along a curved path. Or feet, or whatever label we are using. The R is the radius of the circle that we're dealing with. Now remember, if you don't remember what the definition of radius is, it's the distance from the center of your circle to the outside of the circle, the edge of the circle. That's the radius. If they provide you the diameter, you need to cut that number in half. Diameter is the number across. Okay? There's a couple other formulas that are based on this, like circumference, and we have, the area formulas. They're all kind of based on these numbers, but radius is probably the most important number of a circle. Now, the theta, that's that angle that you're seeing there. The theta that's sitting here is an angle. Okay, its angle is in radians. That's why we've been working with how to convert things. So, if you don't remember how to convert degrees into radians, you multiply by pi over 180. That's the conversion. So that's what we're basically doing for most of the problems today. I got three kind of problems I've kind of picked from the textbook that I kind of just want to go through. There is a clock problem. There is a globe problem where it's an actual real based problem. And then there's a problem where we're dealing with just like a Ferris wheel or something spinning like a car tire or something like that. So we'll kind of mess with each type. And your homework tomorrow is based on these exact problems. So the first ones... you're basically just going to use the formula. There's a couple where you have to do a little bit of extra work, but yeah, it's pretty basic. I think it's about 6 or 7 problems tomorrow on the homework. That'll be a Google form again, but this is the formula you're using in every single one. Okay, questions before we begin? Okay, let's just jump right in. I got 3 problems I kind of want to walk through today. They're pretty straightforward. So let's start with the first one. The first one's based on a clock. So I want to kind of focus on that one. So let's say you had a certain hand on a clock. Okay, so you have a minute, an hour hand. Let's say we're just doing the minute hand. And what time is this clock start? So let's say it's 9 o'clock here. So it's, I guess, 10 o'clock really. Let's say it's 10 o'clock. All right, so let's say it's 10 o'clock and the minute hand traveled, I don't know, let's say 25 minutes. So it's pointing down here. So it went from 10 to 10:25. Okay, and I want to know kind of what angle did it go through? That's number one. What angle does it actually pass through? And then the second part is now that we're getting down to that number, what distance did the hand actually travel? So there's 2 things we want to find. We want to find this number right here, this angle. So the actual angle that's involved that you actually turned. And then the distance that you traveled along that circular path, this distance. If you were staying on the edge of that, the clock hand. Or if that was a car tire, how far did you rotate on the ground? How far did you roll? That type of thing. Okay. Now, I know this seems really weird when they say 10 to 10:25 and you're trying to figure out an angle, right? Because they didn't give you an angle. It's not a perfect 180 if you agree. It didn't go down to 10:30. That'd be a perfect 180. We were just shy of that. So we know the angle's less than 180 degrees. We know that. Here's the best way that I think the fastest way that I would do this. Maybe it's not the best way, but it's the fastest way. I would think about a clock. So if you look up there at the actual clock you're looking at, when you get down to 10:25, do you agree that we're hitting the 5 on the clock?
Oh, yeah.
All right, that's 10:25. The minute hand would hit the 5. right? And so that is 5 out of 12 for going all the way around the clock. So let me write that down. That is 5 out of 12 for a rotation. If it got to 12, it went all the way around 360. Agreed? I did 5 out of 12. That's 1025, right? And so what that is in terms of rotation, it's 5 out of 12 for a total 360 degrees. So that's a fraction of 360. And this will tell me my number. So that's like the easiest way I can tell you how to find the angle you travel through. You know, if you went 12 out of 12, what is 12 divided by 12? It's 1. And you take that times just 1. 12 divided by 12 is 1. You take that times 360 and you get 360 degrees, right? That's a full rotation. If I did 5 out of 12, it's nearly half, of 360, which is nearly 180. So now how you do this in terms of numbers, and this is what I do every single time. I just look at the minutes, what I landed on out of the total of 12. So 5 out of 12, I'm going to take that times 360, and this will tell me my angle I'm going at. So 5 times 360 and divide by 12. You always take the number times the top. So 360 times 5 divided by 12, I'm getting 150 degrees. Now, let's stop and kind of smell the roses at this point. Does that number make sense for my drawing, the 150 degrees?
Yeah.
Yeah, it was. I said it was going to be less than 180. It was. And it would get you to the whatever number you needed to. So get you to the 5. Now, there's a bunch of different ways you could do this. You know, I did it this way. That's the way that I think of clocks, right? It's 5 out of 12. You take that times 360 and it tells you an angle you're traveling through. Some people just go, okay, well, every 5 minutes on a clock is so many degrees. So you just count, how many degrees you're going. 360 divided by 12. Every 5 minutes is 30 degrees. That's another way that some people think of it. That way it adds up to be a total of 360 when you get all the way around. So every 5 minutes. So there's a bunch of different ways to doing it. I just like this way. I like the fraction idea. I think it's quick. It's easy. You don't have to think about it. It's just you did 5 out of 12 and you take it times 360. If you landed on the 6, it's 6 out of 12 times 360. And it would give you the 180. Right? But you can do that for anything. This even works for or hour hands. So maybe you're going to the 3rd hour. Fine. 3 out of 12 times 360. Right? And that would tell you what number you landed. It would be 90 degrees. Okay, does that make sense for the numbers wise anyway? Now, we're going to plug that number in the actual formula here in a second. We need a radius of my clock hand, so you guys get to pick a number. How long of the minute hand do you want to pick?
5,213.
Okay. Whoa. All right, we really committed on that one. So the radius of my clock hand, going from the center to the outside, 5,200. What was the number?
13.
13. Okay, 13. Let's say it's millimeters. It's a really big clock hand.
I was going for
feet. Oh, okay, we'll go feet. I'll go feet. We'll stick with what you want. Okay, so we got 5,213. That's a really bad 213, but we're going to plug this into my formula. So again, if you don't remember the formula from the first page, this is the formula we're using. I want to figure out the distance I'm traveling along that circular path. How far did the minute hand actually drag across that circle? So the radius of my circle is the 5,213 feet. We're going to take that times my angle, but my angle has to be in radians. So we had 150 degrees, right? That was my angle. To convert that to radians, you take it times pi divided by 180. And that's the conversion we did last week. That was the Google question of the day we did last Thursday? That was a Google question, or it was last Wednesday. I think it was Wednesday. It was a Google question. So, but yeah, that's what we have to do. So if we just multiply this straight across, when we convert this to radians, radians doesn't have a label, so the only label that sticks around is the feet label. So that's the beauty of having radians. That's why they actually want it in radians. So I'm taking the 5,213, that's that number, times 150, times pi, and then dividing by 180, right? So now, the decimal that you're going to get in terms of feet that we covered was 13,647.6 feet, if I round it. That's the decimal approximation. If you want the exact answer, 5,213 times 150, this is the exact answer if you want the exact number. I took the 5,213 times 150, and then just left the pi on the top and left the 180 on the bottom. Didn't actually divide them, didn't multiply the pi. This is the exact answer. This is the decimal of what it represents, if that makes any sense. I like to have both sometimes, because maybe sometimes I need to be a little more accurate for the next couple steps, so maybe I'll leave it as a fraction for a while to use it. But if you want just the decimal to get as close as you can, I would just, multiply and divide. Again, calculator will be kind of your best friend when you do these activities with these. Now, that was a pretty big number, agreed? Like that 5,213, I mean, we're generally doing a mile there, and you're going 1 mile in terms of radius, and then you're spinning a big circle. So yeah, you're traveling a really long distance in terms of, in terms of arc. So it makes sense. 150 degrees, that's nearly like 3 radians. It's really close to 3 radians. So that's a pretty big distance. Radian, remember, if you don't remember what a radian is, it's traveling the same distance as your radius. So having 150 degrees is nearly 3 radians, so it's 3 times 5,000, so it's really close to 15,000. So it made sense. 3 radians is like 171 degrees or something like that. Because every radian's 57, so it's really close. That's how I like ballpark it in my head. All right, questions with this this clock problem?
No.
Okay. There's kind of solved the same way. They'll tell you some clock is turning. They'll tell you where it stops. I just use that whole fraction idea. That's the easiest way I do it. I guess this is probably the only challenging part of that whole problem. Is just this part, understanding how that works. Okay. Next problem. Let's do a globe problem. This is really what Google does when you actually research distances between towns. So this is like a real number that Google actually researches and calculates in like the split milliseconds that you type it. So let's say we're on a globe, and I'm going to do my best I can to draw this. So let's say you're on the Earth. So here's the spherical Earth, and I know Earth is not perfectly spherical, but you get the idea. So here's the equator, and the United States is up here. Try to do my best to draw the United States. All right, there's the United States. All right, so there's the United States. Looks terrible, but anyway. So there's the United States, and the idea is that let's say we're going to be traveling from like, we'll just go like something easy, like Garner to Ames, Iowa, right? So Garner, and I'll put these as red dots here, and I'll zoom in here in a second. So here's Garner, and here's Ames. So they're like super close together. Okay. In terms of just number here, let me zoom in there. All right, so there's Garner to Ames, Iowa, and the idea is that that's a distance, right? It's a pretty big number, and so how this is actually calculated is what they do is they find the angle that you're traveling along on the globe, and how they do an angle, and that's what latitude and longitude are. This is something that a lot of people don't understand. Is like, what is latitude and longitude? They know it's like a grid wrapped around the Earth, but they don't understand what the numbers mean, right? So, the equator is a latitude number, right? Latitude is the rungs of a ladder. That's how I always remember it. So when you go up and you go to the next rung, they say this is like 10 degrees, right? I made that number up. And then the next number is 20 degrees, and then 30 degrees, and they keep going. But what most people don't know is like, why is that 10 degrees? Like, what does that even mean? Like, it's just a number, a figment, like just a random number they pick for the next line. No. Here's what it actually means. And this is the part that a lot of people don't even realize. If you were to like cut through the middle of the Earth, like make a snapshot of the Earth and cut it right through the core. So this is a cut, and this is the core of the Earth. And here is, the next layer, and then you have the mantle and whatnot, and you have the, and you go all the way out. And I'm going to exaggerate this. And here is the equator. That's the equator, and the equator goes all the way around. And then this is maybe that next rung of the latitude, which they said was 10 degrees, right? That's that next rung of latitude. And I'm super exaggerating this. This is the angle they're talking about. It's the angle from the core of the Earth out to the crust. So the equator up to that next line, that would be 10 degrees. Now exaggerated. That looks like 60 degrees to me. But do you get the idea? Like, it's how they're making that angle. So every rung of the next, latitude is that big of an angle from the core of the Earth. So when you get up to the North Pole, that's exactly 90 degrees from the equator, from the core of the Earth up.
How do they find those angles?
How?
Yeah.
Well, it's just in terms of number, it's based on this formula. So they know that they can go so many miles up, and that'll hit 10 degrees exactly because of the number, the actual formula we're using here. So, yeah, in fact, you're about to see it, the formula, how it's used. So, but we're going to do it for Ames to Garner. Okay. So when you look at Ames and Garner, so if somebody has a Chromebook, so here's what I need. I need you to tell me the latitude and longitude of Garner. Okay. So just type in Google. Anyone else have a Chromebook that can?
Yeah.
Okay. Type in Ames, Iowa. He's doing Garner. I need Ames, and I need the latitude and longitude. So actually type in latitude, longitude, Garner, Iowa, Ames, Iowa, or vice versa. You have Ames. You're doing Ames. He's doing Garner. And I just need those two numbers. So here's Ames, and here's Garner. Okay. And I need those numbers. And this seems really complicated until you see like how simple and short and sweet it is. Okay, so do we have Garner?
Yeah.
Okay, what do you get?
43.1 degrees north, and then 93.6 degrees west.
93.6 degrees west. Okay, and there's usually a lot of numbers on that, but that's fine. Keep going. Ames.
42.0308 degrees north. And
08 degrees north. Okay.
Just round it.
and 93.6319.
Okay, yeah, I'll just say 96 degrees west. All right. Okay, so what you're looking at here is the difference in angle. Okay, now if I rounded this off, these numbers are nearly identical. I know they had a bunch of numbers after it. Ames and Garner are nearly directly straight north of each other. How I know that? They're on the same west number from the prime meridian. The prime meridian starts in like Greenwich, England, and kind of goes around the globe going, east to west. It's just vertical lines, that's longitude. And so the longitude line is nearly identical for Garner and Ames. So they're directly straight north and south of each other because they're on the same longitude line. So this is the only number that's actually important between Ames and Garner. It's this number. It's the difference in angle. It's the difference in longitude. So I'm going to exaggerate with my drawing over here. Instead of equator, let's say this is Ames and this is Garner. Garner's further north. So Garner was at 43.1 degrees north, and 43.1 degrees north, and Ames was at 42.03 degrees. So there's a difference in about 1 degree, a little bit extra. So if I actually subtract that 43.1 minus the 42.03, the difference in that angle here, this difference is 1.07 degrees difference. That doesn't seem like a big number, like it's 1 degree on a protractor. That's a really small angle. But in terms of distance on the Earth, this distance you're actually traveling, it's a long ways. Because what you have to think about is that the radius of your Earth is huge, right? The distance from the actual mantle, the crust, all the way to the core of the Earth is like 3,950 or 60 miles. It's really thick, right to the actual core. So I'm gonna use that number. Now the number that it's in most textbooks is 3,960 miles thick. That's the radius. So if I was doing my formula here, this formula right here, my radius is the 3,960 miles, and I take it times my angle. Well, what was my angle, the difference between Ames and Garner? 1.07. It's the 1 degree. So it's 1.07 times pi divided by 180, right? Because I have to convert that to radians. Because this was 1 degree, right? So I have to convert that to a radian. Doesn't seem like a big number, but in terms of distance, it's a pretty big distance. So 3,960 times 1.07 times pi divided by 180, and according to this chart, it's 73.95 miles. That's the distance from Garner to Ames, which is actually really close. So, anyone, like, if you guys still have Google, you want to type in, like, distance from...
Whoa, that's cool.
Is it really accurate?
No, I looked up, how long is 1 degree latitude?
69 miles.
69.
It's like 69 miles?
Yeah,
Huh, well, there you go.
and it's 73.83.
Yeah, so, yeah, we were nearly 1 degree, we were 1.1, so 73 made sense. So...
I just thought it was cool. It was like 69.
Yeah, this is actually the real formula that Google uses to actually calculate distances between towns. A lot of people don't know that. This is what they go off of. Now, obviously, what you guys said, like the critical information you guys said earlier was, we're severely rounding these numbers off, right? When you looked at the latitude and longitude number, there was like 10 decimal places.
There's like 4 on Google.
Yeah, 4 on Google, but if you actually go, they go up to 10 decimal places on most websites. And then when it calculates that distance, it's way more accurate than that. That's actually still pretty accurate for just rounding. So that can give you a distance. Now, that's just going north and south. If you went east and west, you have to do the whole Pythagorean theorem, and it's a lot of work. I'm just going to stick with north and south for right now.
Do you know that 1 degree latitude is longer than 1 degree longitude?
Latitude is more than longitude?
Yeah.
Well, it kind of makes sense in terms of that the Earth is actually like it's compressed a little bit north and south versus east and west. We're pulled almost like a football, just because we're on the galactic plane with all the other planets, so we're kind of being stretched a little bit using global tiding. So yeah, it's off by. I think the difference between north and south and east and west in terms of radius is like 25
It
miles.
said 74.05.
So, is that what it says according to Google Maps? Is that what it
Yeah,
says?
I'm talking like just straight.
Oh, straight.
It says 74.05.
Okay, that's pretty good. Pretty close. So, okay, all right. Is there any questions with this one? Okay, last problem of the day. If we do the Ferris wheel problem, so I'm going to get away from all these difficult problems now. Let's do something easy. If we're on a Ferris wheel or a car and we're going to spin so many revolutions, I think an example I did a couple years ago is I talked about a CD-ROM. If you were to put like a CD in a CD player, it spins at so many RPMs, like 10,000, 12,000 RPMs. That means revolutions per minute. It does a lot so that it can read the data. There's a lot of data compressed on CDs and disk drives and other things. Now we're moving to like solid state drives, which are way more accurate and way faster because there's no moving parts. But back in the day, they just had platters that spun and you read data using a needle. And so it's like a vinyl record. That's kind of how it works. Vinyl turns at either 35 or 72 RPMs, depending on what type of vinyl you have. But if we're on a Ferris wheel, this is the example I think I did last Thursday, right? Whatever size of Ferris wheel you have, okay. Let's say it's a 15-foot Ferris wheel. And you're going to spin 4 times. Okay, four complete revolutions. 4 revolutions. We can figure out the distance you actually travel along your circular path. How far would your Apple Watch tell you that you just traveled? Right? Because that's what happened to me. That's the only reason why I kind of paid attention to this stuff. So the formula here. This is the same formula. My radius is the radius is the 15 feet. Now my angle. If I did 4 revolutions, that's 4 360s. That's a full circle's 360. So if I did 4 of them, 4 times 360, it's 1440. Again, how I figure that out, 4 revolutions times 360 is 1440. So that's my angle in terms of degrees. I have to take that times pi divided by 180, and this will convert it to radians, and then I can figure out the distance I actually travel along a circular path. So the distance I traveled, 15 times 1440 times pi divided by 180. I'm traveling 376.99 feet. Pretty big distance. Okay. So in terms of, it's nearly a 1/10 of a mile. So I'm just traveling nearly a 1/10. It's a pretty big number. A lot of people just don't understand like the distance involved there. Just shy of 1/10 of a mile. So, and that was just 4 revolutions. If you go on a Ferris wheel, usually Ferris wheels are way bigger than that. and they spin more times than what you think. So you can travel a pretty long distance. Same with like a car tire. Car tire spins quite a few times, you know, to get you to your destination. Like the distance you're traveling is pretty impressive when you actually look at that in terms of, you know, rotations. So.
What?
Okay.
You did the 4 times 360?
Yeah.
At the top.
Yeah, to find my angle, 4 revolutions is 4 360s, so that's the 1440. Okay, you have a Google question of the day that went live. I think it went live about 5-6 minutes ago. It's just based on a clock hand, so if you want, I can go back to my clock problem. You have to calculate, you know, the distance your hand traveled. I give you a certain length of the clock hand, so I'll go back to the clock problem. So here it is. You have to calculate the distance the angle that your clock hand is traveling at. So figure out, you know, which minute you'd land on, you know, which mark you'd land on the clock. Divided by 12 to figure out, you know, what your angle is. Take it times 360. Then plug in your radius and go from there. So I'm just going to leave this on the board because this is my example. But you can do this for minutes or hour hands or whatever you want to do. So yes. So. I think it's hour. I think you use the minute hand. I think. I don't know if I. What was the number I said for the one on your Google question? Minute hand moved from what?
12 to 3.
12 to 3. Okay, so you're going from noon to, or I guess the right at the top, so like 10 o'clock to 10:15. Move to the 3. The 3 on the actual like clock hand. So mine, I went to the 5. You guys are going to the 3. So yours should be a little bit easier to calculate.
So are you talking like 12?
12 to the 3.
Oh, just the 3? I thought you were talking like...
No, not like full revolutions.
Okay,
Just
my
the-
answer changes. My bad.
I was gonna say, your number would get out.
Shut up.
All right, but that's it for today. That's all I got.
Okay.
So we'll have an assignment tomorrow. Ooh. Basketball tomorrow night. I think the JJV boys game tonight at Newman was postponed, so I don't think Newman play that game tonight. Do we have wrestling tomorrow or is it tonight? No idea. What was that?
May I go talk to Mr. Omens real quick?
You want me to call him and see if he's available?
No, he'll be available.
Are you sure?
Oh yeah.
He does.
Okay. All right.
He doesn't give me.
Laura, do you think Matt will give us Saturday off in practice?